a fighter plane with wooden parts. Have you ever thought about this? If you think this is completely normal, please comment one. During World War II, many fighter planes took to the skies and caused terror. Among them was the Havilland Mosquito. In 1941, it was considered one of the fast operational aircraft in the world. This twin-engine, multi-role fighter was a pride of the British Empire, and one of its special features was that the airframe was mainly made of wood. That's why the Havilland Mosquito was also nicknamed the Wooden Wonder or Mossy. With its groundbreaking design and a speed of over 400 mph, it not only challenged, but also surpassed many metal aircraft of its time. Discover the inspiring story of how a plane made of wood changed the face of war. Revolutionary wooden construction. The de Havilland Mosquito aircraft represented a remarkable achievement in wooden aircraft construction. The airframe utilized an innovative combination of woods, specifically Alaskan spruce, English ash, Canadian birch fir, and Ecuadorian balsa. The Mosquito's groundbreaking construction utilized an innovative composite sandwich design that set it apart from traditional aircraft of its time. At the core of this design was the fuselage, crafted with remarkable precision and ingenuity. It incorporated a 9.5 mm layer of Ecuadorian balsa wood, nestled between the outer skins of Canadian birch plywood, which ranged in thickness from 4.5 mm to 6 mm. This clever combination of materials created a lightweight yet robust structure capable of withstanding the intense demands of combat. As production progressed, the composition of the plywood evolved to adapt to resource shortages during wartime. While early models relied on a mix of birch and balsa, later versions transitioned to birch and spruce due to the dwindling availability of balsa wood. Alongside the fuselage, other essential wooden components played critical roles in the aircraft's performance and durability. Baltic birch plywood, meticulously crafted to 6v3 specifications, formed the backbone of many structural elements. Alaskan spruce provided the necessary strength for key load-bearing components, while English ash was strategically employed to reinforce areas under high stress. This innovative approach to material selection and construction not only highlighted Mosquito's engineering brilliance, but also demonstrated how resourcefulness and adaptability could overcome the challenges of war. The manufacturing process incorporated groundbreaking methods for wooden aircraft construction. The fuselage was built as a frameless monocoque shell, divided into two vertical halves, and formed over mahogany or concrete molds. Furthermore, approximately 30,000 brass wood screws reinforced the glue joints in each wing, with an additional 20,000 screws strengthening the fuselage and empennage. The Mosquito's weight-saving design was a triumph of engineering ingenuity, demonstrating how innovative structural solutions could optimize performance without compromising strength. One of the most striking features was the wing construction, which employed a one-piece wooden cantilever design. This advanced approach integrated two robust box bars that spanned the full width of the wing, ensuring exceptional structural stability. To further enhance efficiency and minimize weight, the top wing skins utilized a cellular structure. This design comprised two thin plywood sheets separated by spruce members running lengthwise, creating a lightweight yet durable framework capable of withstanding aerodynamic stresses. Every element of the aircraft was meticulously designed to balance strength and weight. The wing skins were crafted from birch plywood reinforced with Douglas fir stringers, effectively distributing loads during flight. The fuselage employed a sandwich configuration of plywood, balsa wood, and plywood, providing a combination of rigidity and weight reduction. To ensure durability in critical areas, components made from English ash were strategically placed to reinforce regions subject to high stress. This reliance on wood not only reduced the aircraft's overall weight, but also opened the door to innovative manufacturing opportunities. The Mosquito's construction techniques enabled factories traditionally focused on furniture and piano production to contribute seamlessly to the war effort. Leveraging the existing expertise of skilled woodworkers allowed for efficient production, rapid scalability, and adaptability across a variety of facilities. This approach underscored the ingenuity behind the Mosquito, transforming it into a lightweight yet formidable asset in the skies. Engineering breakthroughs. Initially, the engineering team at de Havilland focused on creating breakthrough aerodynamic solutions for their wooden aircraft design. The British Mosquito aircraft incorporated several innovative features that set it apart from conventional metal fighters of the era. The Mosquito aircraft utilized leading-edge radiators instead of traditional underwing configuration, significantly reducing drag. Moreover, the engineering team designed elongated engine nacelles that improved airflow characteristics around the fuselage. The wing design featured a thickness-to-chord ratio of 13%, which represented a remarkable 28% reduction compared to contemporary aircraft like the Beef 110. To ensure both structural integrity and exceptional performance, the engineering team implemented cutting-edge composite manufacturing techniques, elevating the Mosquito to a class of its own. A critical innovation was the adaptation of resin transfer infusion technology, a process that allowed for the creation of a lightweight yet incredibly strong framework. This technique enabled the precise integration of multiple materials, resulting in a cohesive structure capable of withstanding the immense stresses associated with high-speed flight. In addition to its advanced construction methods, the Mosquito featured forward-thinking design elements that further enhanced its capabilities. Advanced mesh networking capabilities were incorporated, enabling seamless communication and coordination between various systems within the aircraft. This innovation laid the foundation for more responsive and efficient operational control, ensuring optimal performance even in complex mission scenarios. The distributed autonomy systems embedded in the design represented another leap forward in engineering. These systems allowed for decentralized decision-making, improving the aircraft's agility and adaptability during flight. Integrated avionics solutions were also a key feature, streamlining the management of navigation, communication, and operational systems. This holistic approach not only enhanced the Mosquito's functionality but also ensured it maintained superior speed and maneuverability in combat conditions. Through these sophisticated structural and technological innovations, the Mosquito epitomized the fusion of ingenuity and practicality, offering a glimpse into the future of aviation while addressing the immediate demands of wartime operations. The Mosquito's exceptional performance resulted from meticulous engineering and innovative design choices, each carefully tailored to optimize its speed, efficiency, and handling. One of the most significant contributors to its aerodynamic superiority was the incorporation of the RAF-30 airfoil. This advanced airfoil design provided an optimized lift-to-drag ratio, striking a perfect balance between lift generation and drag reduction. The result was an aircraft capable of maintaining high speeds while achieving remarkable stability and efficiency during flight. Another critical enhancement was the use of extended engine nacelles, which played a pivotal role in improving overall aerodynamics. By elongating the nacelles, the designers were able to minimize tail buffeting, a phenomenon caused by turbulence generated by the engines. This refinement not only enhanced the aircraft's stability, but also contributed to smoother handling and better control, particularly during high-speed operations. Additionally, the Mosquito leveraged the Meredith effect, an innovative approach to cooling efficiency. By designing the radiator system to harness the engine-generated heat, the engineers transformed waste heat into additional thrust. This clever integration improved engine cooling and enhanced overall performance, allowing the Mosquito to achieve higher speeds with improved fuel efficiency. The design team employed sophisticated digital applications and agile design principles to generate crucial performance data. Notably, the integration of these features resulted in a maximum speed exceeding 400 miles per hour and a range of more than 1,000 miles with a 4,000-pound bomb load. The engineering team also addressed potential stability issues through careful aerodynamic refinements. Therefore, they installed non-retractable slots on the inner engine nacelles and tailplane leading edge to smooth airflow and prevent localized stall conditions. The complete avionics system, including power and lighting integration, was designed to work cohesively with the ground control station. The success of these engineering breakthroughs became evident as the Mosquito fighter aircraft demonstrated superior performance compared to contemporary metal aircraft. The combination of innovative aerodynamics, structural integrity solutions, and performance-enhancing features created an aircraft that effectively balanced speed, range, and payload capabilities. Performance advantages. The remarkable performance capabilities of the British Mosquito aircraft became evident in 1941 as it emerged as one of the fastest operational aircraft worldwide. The Mosquito aircraft demonstrated exceptional speed characteristics, achieving a maximum velocity of 415 mph. Notably, it could outpace the Messerschmitt Beef 109, reaching speeds approximately 20 to 70 mph faster than its German counterpart. The aircraft maintained optimal cruising speed at 200 mph for maximum range efficiency, although it could sustain higher cruising speeds of 325 mph when necessary. The Mosquito was renowned for its impressive performance metrics, which set it apart from other aircraft of its era. With a maximum speed of 415 mph, it demonstrated unparalleled swiftness, allowing it to outrun many adversaries and excel in various roles. Its cruising speed of 325 mph ensured sustained efficiency during longer missions, making it a versatile asset in combat and reconnaissance operations. The aircraft's capabilities extended to remarkable altitudes, with the service ceiling reaching an impressive 37,000 feet. This allowed it to operate effectively above the range of many enemy defenses. Furthermore, its initial climb rate of 2,880 feet per minute showcased its rapid ascent capabilities, enabling it to reach operational altitudes swiftly and maintain a tactical advantage. These exceptional performance characteristics underscored the Mosquito's reputation as a groundbreaking feat of aviation engineering. The Mosquito fighter aircraft was celebrated for its exceptional handling characteristics, which made it a versatile and formidable presence across a wide range of altitudes. At lower altitudes, its control surfaces were light and highly responsive, providing pilots with excellent maneuverability and precision. This responsiveness was particularly advantageous during dogfights or ground attack missions, where agility was crucial. The aircraft also exhibited smooth stall characteristics, with a gentle nose drop recovery that allowed for seamless regaining of control, even in challenging situations. Additionally, the Mosquito excelled in cornering at speeds below 200 mph, offering pilots an edge in tight, low-speed turns that demanded quick reflexes and steady handling. As the altitude increased, the Mosquito's performance naturally evolved, reflecting the challenges of operating at higher elevations. Above 25,000 feet, its maneuverability began to diminish slightly, with aileron controls feeling less responsive. This mushier control, while noticeable, did not undermine the aircraft's overall capabilities. Even at these heights, the Mosquito retained an advantage that set it apart from many contemporaries: its ability to accelerate rapidly in slight dives. This feature allowed the Mosquito to outpace many single-engine fighters, providing an effective means of evasion or pursuit when speed was critical. Overall, the Mosquito's handling was a masterclass in design balance, offering pilots both agility and reliability. Its ability to adapt to varying altitudes and maintain superior acceleration underlined its status as one of the most innovative and effective aircraft of its time. The de Havilland Mosquito aircraft set new benchmarks for operational range and payload capacity, showcasing an extraordinary combination of endurance and versatility. With its standard fuel load, the Mosquito could achieve an impressive operational range of 1,300 miles, making it suitable for a wide array of missions, from long-range reconnaissance to precision bombing runs. This range allowed it to penetrate deep into enemy territory, often completing missions that were beyond the capabilities of many other aircraft of its era. One of the Mosquito's defining strengths was its ability to carry a substantial payload without compromising performance. Its internal bomb bay could hold up to 1,000 pounds of ordnance, enabling it to deliver powerful strikes against high-value targets. Additionally, the aircraft's design included under-wing hardpoints that provided an extra 1,000 pounds of carrying capacity, further enhancing its flexibility in combat scenarios. The Mosquito's adaptability extended to its armament as well. It could be equipped with a formidable array of weaponry, including 4 20mm cannons mounted in the fuselage and 4.303 caliber machine guns. This armament configuration made it a deadly opponent in air-to-air engagements, while also allowing it to excel in strafing ground targets with devastating precision. Undoubtedly, one of the most impressive achievements was the aircraft's ability to carry twice its designed bomb load. The FBM K.VI variant, equipped with Merlin Mk.23 or Mk.25 engines, could transport to 2,000 libs or 8 rams or 8 rate-ride guided rockets. The Mosquito aircraft's performance envelope expanded further with subsequent modifications. The B.XV variant demonstrated the capability to carry a 4,000 eel bomb load while maintaining a speed of 416 mph, establishing it as an exceptionally effective strike platform. Overall, this combination of speed, range, and payload capacity made the Mosquito aircraft particularly successful in precision attack missions, achieving the lowest loss rate, 0.63%, among all British Bomber Command aircraft. Technical specifications. The technical specifications of the day Havilland Mosquito aircraft showcased the remarkable engineering achievements that made it a formidable combat aircraft. The detailed specifications reveal how this wooden wonder achieved its exceptional performance capabilities. The Mosquito aircraft was powered by the renowned Rolls-Royce Merlin engines, which served as the beating heart of its remarkable performance. Each engine was a liquid-cooled V12 configuration, known for its reliability, power, and efficiency. These engines were capable of producing 1,690 horsepower apiece, a substantial amount of power that enabled the Mosquito to achieve high speeds and exceptional acceleration, making it one of the fastest and most agile aircraft of its era. The Rolls-Royce Merlin engines featured a two-stage supercharger system, a vital component that enhanced their performance at various altitudes. This system allowed the engines to maintain optimal power output, ensuring the aircraft could operate efficiently from sea level up to high altitudes, where many other engines would begin to struggle. The two-stage supercharger allowed for improved engine performance under different atmospheric conditions, ensuring that the Mosquito could retain its superior speed and agility even when flying at higher elevations or in less than ideal conditions. This engine configuration, combined with the aircraft's lightweight construction and aerodynamic design, contributed significantly to the Mosquito's remarkable versatility. Whether engaging in high-speed strikes, reconnaissance missions, or evasive maneuvers in combat, the powerful Rolls-Royce Merlin engines provided the Mosquito with the propulsion necessary to dominate the skies and outperform many of its contemporaries. The airframe incorporated distinctive design elements that set it apart from conventional aircraft. The fuselage utilized a frameless monocoque shell construction, built in two vertically separate halves. Essential measurements included: length, 44 feet 6 inches. Wingspan, 54 feet 2 inches. Empty weight, 14,300 pounds. Loaded weight, 18,100 pounds. The oval section fuselage featured a large ventral section cut out, subsequently reinforced to accommodate the wing center section mounting. The design incorporated a ply-balsa-ply monocoque structure with doped fabric covering, primarily ensuring excellent aerodynamic performance coupled with minimal weight. The combat systems configuration of the Mosquito FBMK.I variant was a testament to its versatility, designed to tackle a wide range of mission types with precision and firepower. This version of the aircraft was equipped with a comprehensive and formidable weapons package that made it highly effective in both air-to-air combat and ground attack operations. One of the standout features was the primary armament, which consisted of four 20mm Hispano cannons mounted in the lower nose of the aircraft. These powerful cannons gave the Mosquito a significant advantage in air combat, enabling it to engage enemy fighters and bombers with devastating force. Their placement in the nose ensured accurate targeting, enhancing the aircraft's lethality when engaging hostile aircraft. Additionally, the aircraft was equipped with four 303 caliber Browning machine guns situated in the middle nose section. These machine guns provided supplemental firepower, further boosting the Mosquito's effectiveness in strafing ground targets and engaging enemy aircraft in close combat. The weapons system supported a maximum bomb load of 4,000 pounds, with the capability to carry various ordnance configurations. The aircraft featured an advanced combat identification system, enabling crews to recognize threats effectively. The technical sophistication extended to the control surfaces, which provided precise handling characteristics, but required careful management at high speeds. The structural design incorporated reinforced mounting points for external stores, essentially allowing flexible mission configurations based on operational requirements. Manufacturing process. The manufacturing process of the British Mosquito aircraft exemplified precision engineering through careful material selection and innovative assembly techniques. The production involved sourcing specific wood types from various global locations to ensure optimal performance characteristics. The construction of the Mosquito aircraft was a highly meticulous process that involved a careful selection of wood from various parts of the world, each chosen for its unique properties and suitability for specific parts of the aircraft. The materials used were not only lightweight but also incredibly strong, designed to meet the demanding specifications required for high-performance military aircraft. Among the key materials was balsa wood, sourced from Ecuador, which served as the core material for the aircraft's structure. Its lightweight nature made it an ideal choice for reducing overall weight without sacrificing strength. Birch, sourced from regions across Canada, the UK, and the US, was used for the plywood skin that covered the aircraft's fuselage. This material was selected for its durability and ability to withstand the stresses of high-speed flight. Alaskan spruce was used for the structural members, providing strength and resilience, while English ash was employed in high-stress areas, reinforcing components that had to endure the greatest forces. Douglas fir, harvested from both the US and Canada, was used for the stringers, the long supportive components that help maintain the aircraft's structural integrity. The selection of these woods was not a simple matter of availability. Only the finest specimens were deemed suitable for aircraft construction. Only 1 in 10 spruce trees met the stringent specifications required to ensure the wood's suitability for aviation. Every piece of wood underwent rigorous testing to verify its strength, density, and grain orientation. These tests were essential to ensure that the materials would hold up under the extreme conditions of flight, meeting the demanding military standards for both performance and durability. This careful attention to material selection and testing played a crucial role in the Mosquito's success, enabling it to perform at the highest levels while maintaining a light and durable structure. The assembly process incorporated sophisticated techniques that set new standards in aircraft manufacturing. The fuselage construction involved forming 2 halves in concrete molds, with each half containing 7 birch plywood formers reinforced with spruce block. Metal clamps held the skin layers tight to the mold as the adhesive cured. Beyond the traditional aircraft manufacturers, the production of the Mosquito aircraft saw significant contributions from industries not typically associated with aviation, such as furniture makers, piano manufacturers, and coach builders. These skilled tradesmen provided essential expertise and resources, playing a key role in the mass production of components for the aircraft. The manufacturing process employed a sophisticated plywood balsa plywood sandwich construction, with thicknesses ranging from 4.5 mm to 6 mm, which was essential for achieving the balance of strength and lightweight properties required for high-performance flight. In total, the assembly of the wings alone required approximately 30,000 brass wood screws, a testament to the precision and care involved in the assembly process. Additionally, another 20,000 screws were used for reinforcing the fuselage and empennage, further enhancing the structural integrity of the aircraft. This collaborative approach to production, which tapped into the skills of various industries, allowed for the rapid and efficient manufacture of the Mosquito. The result was a well-built, versatile aircraft that combined cutting-edge design with the expertise of craftsmen from diverse fields, contributing to its success during World War II. Quality assurance was a vital aspect of the Mosquito's manufacturing process, ensuring that every component met the high standards required for military aviation. The approach to quality control involved a thorough and systematic inspection of both materials and assembly procedures, ensuring that each step of the production adhered to strict guidelines. To begin with, adhesive performance was a key area of focus. Initially, casein-based adhesives were used for bonding materials, but as the need for increased durability became apparent, the production process transitioned to synthetic urea formaldehyde adhesives, known as aerolite. This shift significantly improved the longevity and strength of the joints, ensuring that the aircraft could withstand the stresses of flight. In addition to adhesive testing, the structural integrity of the Mosquito was rigorously assessed. Glue joints were tested under a range of environmental conditions to ensure they could endure extreme temperatures and humidity. The alignment and density of the wood grain were also carefully verified to ensure that the materials would perform optimally under the high stress of flight. Furthermore, the placement and tensioning of screws were inspected to guarantee that each fastener was properly positioned and tightened, securing the structural components and preventing any potential weaknesses. The manufacturing facilities operated under strict quality control guidelines, with each component undergoing multiple inspection stages before final assembly. The production process demonstrated remarkable efficiency, enabling construction at 9 different sites across 3 countries. The assembly process concluded with the application of mandapolum covering material, providing additional structural integrity and weather protection. The manufacturing technique proved so effective that it caught the attention of modern aircraft manufacturers, who recognized its relevance to contemporary composite construction methods. Design evolution. The evolution of the de Havilland Mosquito aircraft stands as a testament to wartime innovation and engineering excellence. From its secretive beginnings to becoming one of the most versatile military aircraft, the design underwent numerous refinements and improvements. The story of the British Mosquito aircraft began in complete secrecy at Salisbury Hall, where the first prototype was crafted using company funds and with an air of confidentiality. The aircraft's development was a highly ambitious endeavor, and the team worked tirelessly to bring it to life. The prototype made its debut flight on November 25, 1940, with Geoffrey de Havilland Jr. at the controls. The results exceeded all expectations during testing, with the aircraft reaching an impressive speed of 388 mph at an altitude of 22,000 feet. By early 1941, the development team had produced 3 distinct prototypes, each designed to fulfill different operational roles. One was a dedicated night fighter, equipped with 4 20mm cannons to engage enemy aircraft under the cover of darkness. Another variant was a high-altitude photographic reconnaissance aircraft, tailored for gathering intelligence from above the range of many enemy defenses. The third prototype was an unarmed light bomber version, designed for precision strikes and versatile enough for a variety of missions. These early variants marked the beginning of what would become one of the most versatile and successful aircraft designs of World War II. The Mosquito's prototype phase was just the start of its evolution, and each version helped refine the aircraft's performance and capabilities. The evolution of the Mosquito aircraft design was primarily shaped by operational experience, with real-world use revealing areas for improvement and refinement. The most successful and widely produced variant was the FBVI, with a total of 2,292 units being built. This version incorporated several key modifications to improve its performance and versatility in combat. One of the notable enhancements was the strengthening of the wing structure, which allowed the aircraft to carry external loads more effectively. This upgrade enabled the Mosquito to carry 2 250-pound bombs internally, expanding its payload capacity and increasing its usefulness in bombing missions. Additionally, the FBVI was equipped with provisions for 8 wing-mounted rockets, giving it added firepower for ground attacks and offering new tactical capabilities. The fighter armament configuration was also enhanced, providing improved firepower for engaging enemy aircraft and supporting its role as a multi-role combat aircraft. The PR-Menk 32 Photo Reconnaissance variant represented a significant advancement, incorporating extended long-span special high-altitude superchargers, hence raising its cruising altitude to 42,000 feet. Meanwhile, the B.XV variant, introduced in February 1944, featured an enlarged bomb bay capable of carrying 4,000-pound blast bombs. The manufacturing process evolved substantially across multiple production facilities. Eventually, more than 400 subcontractors contributed to component production in England. The production of the Mosquito fighter aircraft expanded to include several countries, each playing a vital role in the manufacturing process. In England, the primary manufacturing of the aircraft took place, with the bulk of its components and assembly being handled there. As the demand for the aircraft grew, production also extended to Canada, where complete aircraft assembly was carried out, helping to meet the need for more units during the war. Later in the conflict, Australia became involved in production, contributing to the aircraft's output and ensuring that the Mosquito could continue to serve effectively as a multi-role asset in the Pacific theater and beyond. Yet, production challenges emerged in different theaters. Primarily, the humid conditions in the China-Burma-India theater led to the failure of the wooden wing spar. This prompted the addition of inspection panels in wing roots for all aircraft destined for Far East operations. The design evolution culminated in more than 30 variants, with production continuing until 1950. Ultimately, a total of 7,781 Mosquito aircraft were manufactured across all variants. The final version in RAF use was the T.35 target tug, which demonstrated the remarkable adaptability of the original design. The Mosquito plane's speed and versatility led to its adoption by numerous nations. Notwithstanding initial skepticism, the aircraft's performance validated de Havilland's innovative approach. Similarly, its success influenced post-war aircraft design, with the concept of high-speed, unarmed bombers continuing in subsequent aircraft development. The British Mosquito aircraft's evolution reflected continuous improvement based on operational feedback and technological advancement. Likewise, each variant incorporated lessons learned from combat experience, resulting in an increasingly effective military platform. The design's adaptability enabled its transformation from a light bomber to a multi-role combat aircraft, establishing new standards for military aviation. Operational history. The de Havilland Mosquito aircraft played a crucial role in various combat operations throughout World War II, excelling in multiple roles such as medium bombing, reconnaissance, tactical strikes, anti-submarine warfare, shipping attacks, and night fighter duties. It began its operational history in 1941 with the first production model serving in reconnaissance missions, followed by bomber variants that conducted daylight raids and precision strikes against enemy targets across Europe. The aircraft's performance was particularly valued in its versatility and handling, which enabled it to evade enemy fighters and flak effectively. In 1942, the Mosquito was publicly announced after a successful raid, and it quickly became integral to the RAF strategy, participating in high-speed bombing raids and night fighter operations. It also played a significant role during Operation Overlord and in tactical support for Allied forces during the invasion of Europe. As the war progressed, Mosquitoes were used for diversionary bombing raids, countering German night fighters and supporting the RAF Bomber Command. Post-1943, Mosquitoes also contributed to the reduction of the U-boat threat, and were deployed in various coastal operations. The aircraft's success as a night fighter was evident, with many skilled pilots achieving significant kill counts. The Mosquito's performance in combat earned it a place as one of the most versatile and successful aircraft of the war, with a remarkably low loss rate in RAF Bomber Command. The Mosquito's service extended beyond World War II, with surplus aircraft used by the nationalist Chinese forces in the late 1940s. It continued to serve in various capacities until the early 1960s. The Mosquito's legacy remains as a symbol of British engineering and innovation during the war. The de Havilland Mosquito proved that innovation can break the mold. With its lightweight wooden construction, it reached speeds of over 415 mph and outperformed its metal counterparts. The aircraft's success came from creative engineering, precise manufacturing, and material choices, making it one of the most versatile planes of World War II. With over 30 variants, it proved adaptable and efficient, achieving a 0.63% loss rate. The Mosquito's design challenged conventions and remains a testament to wartime ingenuity. What's your take on the Mosquito's use of wood in its design? Share your thoughts in the comments. Thank you for watching.